Hi folks, this is a short video on the constant velocity joint that is available in Catia V5. It's a fairly elementary introduction, and I want to raise some issues that cannot be found in other videos that are available on this topic on YouTube. Now, first of all, you are probably familiar with the universal joint that's shown at the bottom left corner of the screen when two shafts are not coaxial, they're not aligned, and you want transfer motion from one to the other one. Uh, there are different ways it can be done. For example, one can use gears, one can use belts, or the alternative is what is called universal joint. A universal joint is consisting of two basically yokes and a cross pin, and is shown on the left side. The issue with the universal joint is that if one of these shafts has a constant velocity, angular velocity, the other shaft where the motion is transferred to does not have a constant uh, uh, speed, but it has fluctuating one. This is why usually one way of achieving a constant velocity, going to a constant velocity, is attached to universal joints like that. Okay, and this is what you traditionally referred to as a constant velocity joint or the double universal joint or double cardan. In Catia, the joints are described here, and notice that there is one that kind of looks, the arc looks kind of looks like this, and this is a constant velocity joint that we're going to be discussing. Now, here is another drawing where you have there is an input shaft, there's an output shaft, and notice that they're not coaxial, they don't have the same axis. But in order to transfer constant input velocity to constant output velocity, one uses this piece in the middle, which actually fluctuates. The velocity of this is not constant. This middle piece is not going to be constant, but it fluctuates. Now, again, a setup like that is called constant velocity joint or double universal joint or double cardan joint. Now, also keep in mind that in the modern cars, there are universal constant velocity joint used, but the setup is quite a bit more complicated than what you see here. This is the most elementary description of the CV joint. Okay. Now, what you see here is the same thing drawn in Catia. So basically, these three will make the constant velocity joint, and of course, you need two revolutes at the end where these are attached to. I have separated these so that you can see what's going on. And the purpose of these grooves here is just to make sure you can see when this thing rotates, revolves. But notice that under two conditions, you can create setups like this. One of them is when these two axes are parallel. And by default, what that means is that all these three pieces lie in the same plane, or their axes lie in the same plane. This is one way of doing it. The alternative is this, which is called half angle constant velocity joint, where again, these three make the universal joint, make the CV joint, and these have to be revolute, and the axis must all be in the same plane, just like before, and these angles must be the same. Okay? So this is the other way. Now, when it comes to modeling this thing, I'm not going to do it with this setup, but we'll do it with the previous one. There is very little elementary information on the mathematics of or the modeling of this is available on the internet, unfortunately. There's a lot of videos, they talk about CB joints and things like that, but not much you can find in books or at least textbooks and on internet. But here's one. Okay? It talks about the setup, and what they do is they run this thing in MATLAB, and notice that we have the one on the top goes when the axes are parallel to each other, and notice that the input and output velocities are lie on top of each other. Okay, and of course these are the for you can see that they're identical, but the input one fluctuates. Sorry, the middle one, the middle piece fluctuates in velocity. Okay, now this is the other setup where you have the angles are the same, but the axes are not parallel, and you can see that pretty much the same behavior, except that the fluctuations are smaller, as you can see. There are two good other good videos on the use of Catia in doing a CV joint that are given here, but once again, it doesn't talk about some of the delicate issues that we have to worry about. And now remember, Catia V5 is buried inside of the 3D experience, and it's referred to as the 3D experience Catia. Okay. Now in there, if you look at the joints, the CV joint has been taken out. So there is a universal joint here, somewhere there, if I can find it. Yeah, there's the universal joint, but the CV joint does not appear in this list. All right, let's go ahead and do it. Dimensions don't matter in this problem, so what I'm going to do is I'm going to make one of those shafts and basically create two instances of it, and one of those yellow pieces that you saw there where the revolute is going to be, and I'll make an instance of it to get the other one. So let's go ahead and insert the first part, new part, in there, and I'm going to call this thing shaft. Properties, I'll call it shaft. Shaft. Okay, let's go make it. Dimensions don't matter. I'm going to go to this part design. On that vertical plane, I will sketch a circle like that, and I will make a slight cut out here, so that you can see actually that the thing is rotating. So it doesn't matter how you do it. The shape of it doesn't matter either. So yeah, I'm going to make it cut out like that. Obviously, I have to clean this up before I'm going to pad it. I'm going to get to this, quick trim that, quick trim this. Yeah, and this. And there. Exit. I'm going to pad it long enough so that I can see it. Let me make this thing 10, see how it looks like. Sure. I'll make it 12. A little bit longer. These dimensions means absolutely nothing. Okay. So this is my shaft. And then I'm going to make what do I make the bearing? So insert, loop. Let's go all the way to the top, all the way to the top. Insert, new part. Say no, and I'm going to change the name of this thing to be bearing. That's the end pieces, where it's going to be revolute. All right, good. Let's go make it. Double click on that plane, on that end plane, to make my job easier. I'm going to sketch a circle and then pad. You can do it any way you want. This is going to be my bearing. Exit, and then pad it. Let me make it a little bit longer. This is going to be the bearing. I'm going to change the color of this so that it can be seen better. Yep. Very good. All the way to the top. Now, I need two instances of the shaft and one instance of this bearing. So how do we do that? We are in assembly design. If it's too much of a hassle, you can do a copy and paste and basically avoid that, but I'd rather use the instances right there. Uh, Here's how you make instances, okay, right there. There is fast multi-instantiation. So whatever number you had before is going to pop up. Notice that it says, okay, this actually does three of them. I'm going to delete one. It doesn't matter. The reason it does three is because fast multi-instantiation. And in my previous run, I made three pieces. That's okay. So it says, okay, pick the thing that you want to make instances of right there. And notice that it made these, but I don't want this last one. I'm going to delete that. And I'll do exactly the same thing, except that I select this piece and it does the three, but I don't want it. That's okay. I'll just delete where are these? Yeah, I just delete these two. Just delete these two. Good, very good. Now I have all the pieces. So what I'm going to do, because I want to make sure that these are all in the same plane. Remember, the caveat here is that these axes of these things must be in the same plane. And by the way, it's the same thing over here, which I'm not going to do. Okay, so let's go back. Because this is the case, it's very easy for me to move these things. Get rid of this. Yeah, and I use here. See that? It's the manipulate, and I'm going to move things in the XZ plane. If I use this icon here, this piece, this selection, then everything will move in the XZ plane, and that's good. That's what I want. So, for example, I'm going to do this is moving in the XZ plane. This is moving in the XZ plane. This is moving in the XZ plane. However, I want to rotate it. Okay, so I'm going to rotate it about the y-axis. That's this, about the y-axis, so that it stays in the XZ plane. You can see that right there. Okay. Uh, if you, yeah, that's fine. So if it's bothering you that these are different, the way that they're drawn different, but that's okay. Now let me move this thing up a little bit. Really doesn't matter, and then we say okay. So what you see there is really this. Okay. So we're going to put assembly constraints here. First thing I'm going to do is I'm going to anchor this bearing, the original bearing. So where are the constraints here? Let's get them out right there. I'm going to anchor fix this bearing. Okay, you can see that. Then I'm going to, because I want a revolute joint later on, I'm going to make a coincidence between the axis of this shaft and the axis of the bearing. This axis and that axis. They're already coincident, but that's okay. And then a coincidence between the end plane, because I want to make that thing a revolute joint. This, let me hide that, and this. So this is going to turn it into a revolute joint later on. Now, let's see for a second. Let me bring this thing so I can see it. Good. Now I want to create an angle of well, by the way, these two are parallel. These two are parallel because I moved things in the XZ plane. Remember that? So I don't really need and to specify this angle. These are the parallel. So let me see now. Now I want to create a revolute there, but let me first create the revolute at this end. Coincidence between this axis and that axis, and coincidence between this plane and that plane. Okay, and of course update. It's going to go there, and now we're going to go and create a rigid between these two end bearings. Okay. So rigid, to do that later, we can clip them together right there with a paper clip fixed together. So I want to fix this with that bearing. So these two bearings are going to be fixed together later on when we create our when we create our joints, it's going to become a rigid joint. All right. Now, we are done here. So we're going to go to, we don't have to do anything with these other pieces. Uh, so let's go ahead to uh, digital markup, DMU kinematics, convert, get the magic wand, use the magic wand, and convert all the constraints that I put in there into joints. There's going to be a revolute here and there's going to be a revolute there, okay? And so to use this market assembly constraint, new mechanism, mechanism one, auto create. So let's see what kind of joints we've got. So we got the revolute here, revolute at the bearing, left bearing, revolute at the right bearing, and a rigid between these two were clipped together with that paper clip. Now we're going to go to our joints right there and use the CV joint. Notice that it's asking you for those three axes. So I select the axis. Make sure you select the axis of the shaft, no, not these lines. Okay, the axis of the shaft for spin one, the axis of the other one for spin two, and the axis of the third one for spin three. In the event that these two are not parallel, or these three things are not in the same plane, you will not be able to select the third spin. For the case that the situation is like this, in the event that these angles are not the same, you will not be able to select the third spin axis. But here, because I only did translation in the XZ plane and moved things around, uh, they these two are parallel and therefore this can be concluded. You say okay? All right. Degree of freedom is 1. So let's go to the revolute, this one, and make it angle driven. Obviously, the mechanism can be simulated, and you can just go ahead and manually move it. Now, in the event that you want to put some physics into it and check the velocities and things like that, that's easy. So I'm going to reset that. We have shown how the CV joint can be created. And I have told you that if these two are not parallel to each other, it's not going to work. Okay? And I have, although I've not done it, I've shown that in this case, if these angles are not the same, and obviously these are not in the same plane, it's not going to work. Okay, now let's put some physics in it and see what's going on. Okay, so here's f of x. Click on the joints. So there is this angle-driven joint. Let me give this thing a speed. So I select that, add a formula equal to, how about 60 RPM? Is that good? 60 RPM, 60 turn underscore minute, or you can write, or you can write, for example, 360 degrees underscore second, etc., multiply by time, and then you say okay. Because later on I want to plot some stuff, let me create some sensors. This is in case I want to plot some stuff, and I do. And for example, I can select for the reference product, I select the left bearing that's fixed. For the point, I'm going to select, for example, I don't know, this point. Good. Let's do another sensor for this end. So another sensor. Reference product is again the bearing, fixed bearing. And for the point, I'm going to select this point. Say okay. Very good. Now we're going to do simulation with loss. Let's do 2 seconds. So this is going to turn twice, maybe 5 seconds, doesn't matter. And activate sensor. And I want to see the angle, for example, the angle of the two revolute joints, this one and that one. Move this thing out of the way and play it. 5 seconds. And let's look at the plot graph of the angle of the two shafts. They coincide. So what you're seeing here is actually these graphs with the middle bar, fluctuating bar is not plotted. Okay, folks? So the moral story is that although this is such a trivial thing that should be described somewhere, the constant velocity joint can be used, but the restriction is that these two axes must be the same, or not the same, but parallel. And in this situation, this setup, these two angles must be the same. If you go and change those angles, if you made and change those angles, or make those slightly off, not parallel, you won't be able to use the CV chart. Hopefully that was useful.